So by the definition, if I have H subset of group G, so that H is subgroup of G, we need to check first is closure, and the second is associative, third is identity, and the fourth is inverses. So this is all is a axiom of group. But I will give a nice terms. So with this theorem, you only need to prove closure and also inverses. So you don't need to prove associative, and also you don't need to prove identity. So this is the theorems. I will call this theorem is subgroup criterion. So in here I have suppose H is non-empty subset G, then H is a subgroup of G if and only if H satisfies the following condition. Okay, the first one is for all A, B in H, then A star B. So this is a binary operation star in H. So this is for closure. And the second is for every A in H. So there is unique A in first in H. So this is for inverses. So before we use this theorem to show that H is subgroup of G, I will prove this theorem. So I will show the proof of this theorem. So in here we have if and only if. So this is two directions. So we need to show two directions. So one direction is we have H is subgroup of G, then H satisfies this condition. And the second direction is if H satisfies this condition, then H is subgroup of G. So I will give a proof for the first direction. So here. So for the first direction, we have H subgroup of G. F is subset of G, and this is H subgroup of G. Then we need to show that H satisfies. The first one is closure, and the second one is inverses. So this proof is very easy. Okay, since H is subgroup of G, then as we know by the definition, H is a group. So because H is group, therefore H satisfies the first one is for all A, B in H, then A star B is also in H because H is group, right? So that's why H is closure, and for every A in H, this exists A inverse in X. Okay, so next we will prove for the left direction. In here I have H subsets of G, and H satisfy. The first one is closure, and the second one is inverses. Then we need to show that H is subgroup of G. So proof. Okay, we take. So we need to prove. So we already have closure, and also we already have inverses. So we need to prove that H is associative, and also H has element identity. Has identity element. So let's A, B, C in H, because since H is subset of G, then A, B, C is also in G. So in here we have A star B star C is equal to A star B star C. Why? Because G is a group. Hence, H is associative. Okay, the second is we need to show that H has identity element. So we know that H has inverses. So for so for every H element H, then we have a inverse in H such that A star A inverse equal to A inverse star A. This is equal to E. This is equal to identity elements. So as we know that H is closure, since H is closure, then identity is also in X. Therefore, we can conclude that H is subgroup of G. This is the end of our proof.